For basically all of human history, getting to space has meant one thing: riding an explosion, right? We strap ourselves to these incredibly complicated, expensive, and honestly pretty terrifying rockets. But what if there was another way? What if we could just build a bridge to the cosmos? Seriously, what if rockets were just obsolete? Imagine getting to space was as simple as pushing a button in an elevator. Now this sounds like pure science fiction, I know, but it's one of the most audacious, mind-blowing engineering projects ever dreamed up. And today, we're going to find out if it's actually possible. I mean, just look at this thing. We're talking about a physical ribbon anchored to the Earth, stretching 100,000 kilometers up into the black. To put that in perspective, that is over a quarter of the way to the moon. And get this isn't just some fantasy drawing. Real organizations are seriously trying to figure out how to build it. So what is it exactly? Well, at its core, it's a super strong cable. It connects the ground to a huge counterweight way out in orbit. We're talking like a captured asteroid or a big space station. And then, electric climbers just zip up and down this cable, carrying cargo, satellites, maybe even us, smoothly and quietly right into space. The potential here could change everything. This isn't just a new kind of rocket, it's a permanent highway to orbit. It could do for the solar system what the railroads did for the continents, unlocking asteroid mining, building giant solar power stations, maybe even our first cities on other planets. Okay, but a dream this big runs into some absolutely colossal challenges. And the very first one is a fight against the most powerful force we know, gravity. How in the world do you build a tower that reaches space without it just falling over? And that's the big question, right? Gravity never quits. How could a cable that long, with its own insane weight, possibly stay up? Well, the secret isn't about pushing up from the ground. It's about pulling from the heavens. The whole trick is this cosmic tug of war. So first, you anchor the cable to the Earth. But then, and this is the key, you extend it way past a magic point in space called geostationary orbit. Out there, the counterweight is moving so fast that it's constantly trying to fling itself into deep space. It's just like swinging a rock on a string. That constant outward pull is what keeps the entire cable perfectly tight, defying gravity. And the magic number, the secret ingredient that makes this whole thing possible, is this: 42,164 kilometers from the center of the Earth. That's it. That is geostationary orbit. So why that number? Well, at that exact altitude, a satellite's speed perfectly matches the Earth's 24-hour spin. So if you look up from the ground, it seems to just hang there, motionless in the sky. By building the elevator around this point, the entire structure spins in perfect sync with our planet. It's a genius balancing act. Okay, so the physics works. Awesome. But that leads us to problem number 2. And honestly, this one's even bigger. It's the real showstopper: finding a material strong enough to actually build this thing. I mean, think about it. The cable isn't just holding up the climbers. It has to support its own ridiculous weight over thousands of kilometers. The tension on this thing would be so huge, it would snap steel, titanium, Kevlar, literally any material used today. It would just snap it like a dry twig. And this chart shows us the real enemy. See, the stress isn't the same all the way up. As you climb, the weight of the cable below you adds more and more strain. The tension just builds and builds and builds until it hits its absolute maximum right at that geostationary orbit point. Any material that can't handle that single point of stress fails. The whole project fails. This is the great filter. So that's the billion-dollar question. What material in the known universe is strong enough, but also light enough, to handle that kind of force? For decades, the answer was nothing. And then, in 1991, everything changed. Scientists discovered this: carbon nanotubes. These are microscopic tubes made of pure carbon, and on paper, they are the miracle material. Theoretically, they are up to 32 times stronger than steel, but they're incredibly light. For a second there, it looked like the biggest hurdle to the space elevator was solved. But of course, the story has a twist. Our hero material, the one thing that could make this dream real, it has a secret, a fatal flaw. As one researcher perfectly put it, our miracle material just isn't cooperating. See, the problem isn't with one single perfect little nanotube. The problem is trying to make a cable out of them that's 100,000 kilometers long. So here's the deal. In the real world, when you try to weave these tiny tubes into a long fiber, you get flaws, little gaps, tiny misalignments, and each one of those tiny flaws weakens the entire cable. We just can't, right now, produce a long strand of this stuff that gets anywhere near its godlike theoretical strength. An expert came up with the perfect analogy for this. They said it's like a run in a stocking. You get one tiny imperfection, and that creates a weak point. And under the insane strain of a space elevator, that one tiny weak point could cause the entire cable to just unzip itself from top to bottom. A total catastrophic failure. So is that it? Does this one fatal flaw mean the whole dream is dead? Is the space elevator actually impossible? Not so fast. The dream isn't dead, it's just getting smarter. Engineers are already working on clever ways around the problem, and they're backed by some very serious money. So if you can't make a perfect cable, you get clever. One idea is to taper it. Make it much thicker at that high stress point in orbit and thinner everywhere else. But then there's an even wilder idea, the orbital ring. Instead of a tower going up, you build a massive magnetic ring around the entire planet in low orbit and then drop cables down to the surface. The debate is on. And don't think this is just theory. The quest is real. Huge Japanese construction firms like Obayashi and Shimizu have publicly said they want to build a space elevator by 2050. You've got materials companies and even giants like SpaceX all exploring these ideas. The race is on. And you know it's getting real when you follow the money. The market for space elevator tech is projected to be worth over $1.16 billion pretty soon. This is moving out of sci-fi and into a serious multi-billion-dollar industry. But all of this, the money, the engineering, it brings us to one final and honestly pretty terrifying question. We've talked about the dream. What about the risk? I mean, we've got to ask, right? After building this incredible structure, what is the absolute nightmare scenario? What happens if, despite everything, the cable snaps? Well, simulations show a two-part disaster. The top part of the cable, the bit with the counterweight, would get flung away by its own momentum, tumbling out into deep space as a massive piece of junk. But the lower section, no longer held tight, would fall. It wouldn't crash in one spot. It would wrap around the Earth like a colossal whip, burning up in a terrifying streak as it rips through the atmosphere. So that's the space elevator. On one hand, it's our stairway to the stars, our ticket to becoming a true multi-planetary species. But on the other, is building it worth the unbelievable risk of it all coming crashing down?